faces. I said a lot of happy faces. It's true.
We may have to back up to show the trebuchet, but that's a... Yeah. Okay, this is the first day of the mechanics course. We've done the review, and now we do the real stuff. And I decided quite a while ago that the trebuchet was, first of all, an interesting machine, and we're going to talk about it for the next 3 lectures in various ways of looking at it. But it also is an excellent introduction to using Lagrangians in a problem that you really don't have any other methods that are just a direct application gives you the best answer you can get. So the basically it's a funny arrangement for a couple pendulum. Obviously, if this thing were to go to equilibrium and hang down there, it would be a form of a double pendulum. But it has an interesting history. It also has some applications to human kinesthetics, that is the ability to be good at sports that involve levers, starting with, say, baseball, tennis, that's my game, golf, lacrosse, quite a few things. And then there's always sword play, that is fencing. All of that involves getting some part of a lever to go really fast without hurting yourself. So we're going to talk about that throughout the discussion here. But the main thing that we need to show is one more derivation of Lagrange's equations in a situation that's complicated, like this is a fairly complicated device. So the idea of that is really important, and then we'll have today a summary of that development and a discussion of what it is that it does and what it is that it doesn't. And then next lecture we'll come back and look a little bit at first of all the generalized curvilinear coordinates in gory detail. I'll have a little bit of it today because I've given you a problem to match covariant quantities with some geometrical links on a coordinate system. I don't know if you've looked at the graphs that come with the homeworks today. And so we'll get started on that a little bit today, but mainly next time it's Unit 3. Unit 2 and Unit 3 kind of go, for a while anyway, on the same subject, but Unit 3 uses more of the generalized curvilinear coordinate geometry, whereas the thing we'll do today doesn't require that. And the other thing that we may be able to look at a little bit is that geometry, the tangent space versus the normal space. Most of that's the second lecture on the trebuchet. Then in the third lecture, we just break it down to the simplest analogs to the motion and analyze those. So let's go ahead and I'm going to back up on this one. We'll track the 2 screens here today. The basic idea here, and we have a simulation here that shows it, and I have a purchased from the Arbor Scientific company a lightweight, also almost balsa wood trebuchet, and we'll compare its motion in just a minute here with the one of the small ones that I built here to demonstrate its capabilities. And This one has wheels, although it really doesn't need them, but that's another degree of freedom that needs to be attached here to get the more advanced trebuchets that were made in the 1500s and late 1400s. So this is a ancient war machine. It's a terrible machine for a number of reasons. One of them is that it's the beginning of biological warfare. As you know from your history studies of the Middle Ages, the ages of feudalism, that there people built for protection huge castles. City-states were within walls, places like Florence and Siena and Italy. You can go there now and see wall after wall after wall, and you get the feeling that these people are really paranoid, but it wasn't paranoia when you have attackers on all sides. But the trebuchet was a way to break the walls down, and that's basically it. But sometimes they couldn't break the walls. So then the plague had come through, so they would throw plague victim bodies into the castle, get them to catch the plague, and then overrun the castle that way. So there's a horrible history for these machines, as for any war machine, really. But right now it's become a recreation. As I say in the textbook, maybe this could be a problem for Galileo. In other words, if you're thinking of how we in science now get a lot of our money from the DOD, maybe that would have happened in thing. It didn't and wouldn't. But Galileo, you can imagine him given the problem to optimize this machine for war purposes. And why wouldn't that have happened? Well, it's simply because basic calculus hadn't been discovered, but at least even more so, we had to wait for Lagrangian calculus, which we're going to use to solve it. There's all sorts of reasons. And then finally, the differential equations which this produces are not analytically solvable. That's a big drawback. So you need to wait until you have a computer to solve them, and that's what we're going to be showing with our simulations here. So really all Galileo could have was, after the trebuchet has been fired, the second arm swings like a pendulum, and he did some wonderful physics by looking at the Sistine Chapel lamp swinging in the breeze that always goes through that building, and worked out the basic idea of a pendulum. So just a simple pendulum in its linear regime is Galileo's start on physics, basic mechanics. Now, this is what we find. The use of the trebuchet now is to get rid of old junk cars, and basically that's what I'm going to be showing with this demonstration. This is very much like this trebuchet that comes from Arbor Scientific. You put it together with glue. You literally cut it out and put it together, which I did over the weekend. And I'm still not used to this trebuchet, but let's take a look at it. It comes with a complicated sheath that releases the mass that it throws, and it involves two monofilament cords. I did not get that to work very well. So what I'm going to do here is I'm going to not only throw this washer, but the string that goes with it. Okay, we'll dispense with the release mechanism, which doesn't work very well. But the basic idea is that, like the one in the photograph on the screen, I'm going to have this will be like that car, that unfortunate car that's sitting waiting at the end of the trebuchet, pretty much underneath the trebuchet. Okay, so you can see that car sitting there, and it's not as far as this washer is here. Car is sitting right about directly under the axle. I've got a lot longer sheath on that thing. Anyway, here we go. 5, 4, 3, 2, 1, 0. That's the throw, okay? And it, you know, it's variable. I do it again, and I could probably hit the board, but that was a kind of a low throw. It sort of sometimes gets a little hooked on the release. So that's what's going on here. Okay, is after this thing drops its weight, the cart is thrown high into the air. This is the thing. Now this has become a hobby, and it's approaching Halloween now, where you have lots of pumpkins. Particularly after Halloween, you have lots of pumpkins you want to throw away. So why not use a trebuchet to throw them away? And I mean far away. And so that's what you find at the World Championship Pumpkin Chunking Contest here. And there's a trebuchet that's just hurled a 20-pound, that's a big pumpkin, to 240 miles an hour, which takes it many hundreds of yards away, more than half a mile, and some of them are trying for a mile. So this is the contestant trebuchets for the thing. And this is just across the border over in Oklahoma that this occurs, as I've told us also occurring in Baltimore, around Baltimore someplace, some park they have there. So this has become quite an obsession. And then it leads to more complicated devices. Okay, the trebuchet maximum range was about 1,200 feet typically. Now they've got these air cannons. And they're, these things can throw a pumpkin 4,000 feet. I think they've thrown them over a mile. So anyway, this is the kind of stuff that, you know, Americans don't have much to do, so here's what they do on Halloween and other times of the year. Okay, so that's kind of amusing. And also, I should point out, let's just see the thing operate here with a simulator. I have an old simulator down at the end of the thing here, but let's just take our new one and throw it. Okay, so there's the thing is wrong. And then these simulations then continue to do the oscillation that follows. It sort of puts the mass back on there, so you keep seeing it repeated. And this is a quasi-period. In fact, it's a periodic trajectory. You don't see periodic trajectories with such a nonlinear system very often. But the other thing that we have right now on this, pause it here and go to controls. I can set it up for the more sophisticated one, which we're going to be talking about in the second lecture, where you really optimize the trebuchet to throw at a castle. And this one was on NOVA, and it was also published in the Smithsonian as a summer project to build a trebuchet and, you know, pretend that you had to knock down this castle. And the wall of a very old castle was there, so they got permission to put a hole in it, or try to put a hole in it. And that really throws the thing. And then when we put the mass on and let it run without friction, this is an ideal trebuchet, this is chaotic motion. This is what you expect from nonlinear 2 or higher dimensional mechanical systems. You will find this kind of thing going on. Okay, it's really quite beautiful. But what you notice is every once in a while it really wings at them. That was a pretty good one right there. That was even better. And you just wait until you see it just in the right position to put a lot of energy. That was pretty good right there. That's not too bad. Right? That was a good one right there, you see. So the lesson from this is, if you're talking about lever sports, is that application of fairly small amount of force can yield a tremendous amplification, nonlinear, parametric amplification of the final result. And that's something we're going to be talking about in the third lecture on this mechanical device. So I'll pause this thing so it doesn't take our time or make us dizzy anymore than I'll have to. But the real thing I want you to see is some history. First of all, I told you the bad history where this thing was used as a biological warfare. But what built our culture? What built us? What makes it possible for us to sit here in an air-conditioned or a heated room, sort of immune to the elements, more or less, right, and study mechanics or whatever? What got us to that? And this is what got us to that, okay? First of all, I had to eat. This is the main one. This was done more than any other of these motions, I would say. Reaping, swinging a scythe. Scythe, if you've ever picked one up, is a pretty heavy piece of equipment. And you got to know how to use it, or you're going to hurt yourself, okay? And the trebuchet motion is what you seek, so that you get a lot of kinetic energy to cut the wheat. But the same thing's true of chopping, or log splitting, or just cultivating and digging in a garden, just plowing it up with a pickaxe. Or if you're building a railroad, you've got to do a lot of hammering. And this was in the 1800s, right? Built the railways for starting in Britain and coming over here to the United States, okay? Southern people are called crackers. Why is that? Because the Spanish cowboys herded cattle with a bullwhip. And that's what we're really talking about here, is the amplification of a whip, the whip action that you get by doing these swinging a lever rapidly, okay? And of course the slingshot, the allegories of David and Goliath, okay? Or just plain pitching and throwing. You're doing that with your arms if you're good at throwing, okay? The idea is to amplify that, you say, with a longer lever. Well, in any case, each one of these activities, we don't have to do them anymore. I mean, if you want to, you can go out and hammer and cultivate and split logs and, oh, that's nice, good exercise, right? You don't have to do it, right? We have machines to do that, right? But we're humans. We learn to do this. Our culture learned to do this. So here you have us every weekend, you see, or every bit of free time. Someone like me doing that, tennis, okay? People that garden are still doing that. If it's a small garden, you don't hire a machine for that. But golf, that's the most addictive of the sports. This is the second most addictive one. Baseball, kind of addictive, but there's a lot more to it than just batting. But you certainly want to be a good batter if you want to play that well. Lacrosse, that's one we don't know too much. That's an Eastern one, right? Then, of course, there's just throwing. How do you throw a football? And then the whip action that you get if you're water skiing. Okay? Those are a couple of the things that are going to play a role, or do play a role, in the motion that the trebuchet has. Okay? And the main thing is that some technique is required to do these. We're going to compare these to ways of throwing things that don't require a lot of technique. And it turns out the trebuchet motion wins in many ways. So this, I think, is really a little bit of human culture here. First of all, building the civilization, and then secondly, we can't stop. Or at least some of us can. Okay, so the first thing that we're going to deal with here is the coordinate geometry. And the basic idea, of course, is that you've already seen this once with respect to polar coordinates, but these coordinates are not orthogonal. They're not the nice kind of coordinates that OCC gives you. So we're going to have, first of all, Jacobian, and then we'll get the generalized velocity, we'll get the kinetic energy. In terms of a metric tensor, we'll do that today, even though that's the venue of unit 3, but for unit 2, we do need that. That is part of the story, and it's not told very well in the mechanics book I've seen. It should be. It really separates and cleans up your approach to any Lagrangian problem. So the generalized force and acceleration, all that is going to come out. We'll I'll be looking at that very shortly here. And here's where we will show, first of all, what coordinates are we going to use for this thing. And the most obvious ones are theta. Now I've drawn this thing a clockwise theta just to be mean, but that's not a bad idea, because you make a minus sign, and I do the same thing with this one. When it's on this side, that's a minus. When it's on this side, that's a plus. But let's put a minus on it so that the minus shows up in the algebra, and then we can check it. That's a good way to avoid errors, is to put the minus in right away and just let things happen and see if you're getting the right answer. So our first geometry is just the sides of the triangle that this has, and it has a minus right there on the cosine, but it already has an x equal r sine of theta, okay, for the distance right there. So that's the beginning. But then it gets complicated, because this angle figures into what this one's going to be. All of these angles are star fixed, inertial frame fixed, okay? Now the Hamiltonian, later on, I'm going to want to do something besides that. But here, this line here, that's the reference line for the angle, is star fixed, okay, lab fixed, okay? And that's the first coordinate, is the theta of the main arm and the big mass. And then it's the little mass, depends on both of the coordinates, and that's what makes this complicated. Okay, and I see some typographical things that did not show up before. Let's see if it's on this machine here. I'm going to back out of the simulation here and see if that's going on. This is more of that font war, the font wars. I think we're much better off on this particular machine. This is a newer machine, and something crazy is going on. I didn't look at the lecture with this machine, but that one's got it right. Okay, so we'll find out what's wrong with that. So let's use this one as the main driver here, and I'll point at it with an ultraviolet or blue laser pointer. In any case, that first triangle we talked about here is right there, and then it's the coordinates of this mass right here that we're talking about. We're talking about the R having raised the point up to here, and then I'm going to go down that line right there to get to my actual mass coordinates for the little mass M. And there's a disadvantage for this particular projector in the sense that the dark, it's so dark you can hardly read the M in there, but you don't need that if you've read. Anyway, these two, this set right here has to be added to those two. Okay, so making a nice clean diagram for this is important. And then this angle right here, the phi angle, okay, I'm showing it with a positive. I could have put it on this side with a negative. This time I left it as a positive. Okay, so basically what we got when we add these two x coordinates and then these two y coordinates is this is the equation on which we're going to differentiate and get our Jacobian. And that's the main thing. Now this is the picture in the textbook. This is maybe a little nicer picture of the geometry that emphasizes how they're being summed to give us the Cartesian coordinates in terms of the generalized coordinates, and there are two generalized coordinates, theta and this phi right here, the swing angle of the second pendulum, you might say. Okay, so taking the differentials of that gives us, well, the partial derivatives are the coefficients here with respect to the big X, and here with respect to the little x, and then the little y, which are the coordinates of this mass right here, relative to the origin of the trebuchet. So that's what we get right there. That's our differential relations. Now, at this point, we have to ask, what's going to be the Jacobian? Because we've got Cartesian x and Cartesian y here, and then we've got Cartesian little x and little y over here. So we've got, in the Cartesian department, 4 variables. So we make a little chart here, and what we get is a rectangular Jacobian, not what you want. We would like to have a square Jacobian. So out of this rectangular Jacobian, we pick 4, shall we say, 4 elements, 2 rows, or 2 blocks. Now this one completely fails. If you do this one right here, because of the x and y not having any dependence on the of the angle phi, you get a 0 column right there. That's a failure. You cannot work with a Jacobian that's 0 everywhere. But you'd better get used to working with Jacobians that are 0 somewhere, and in fact Jacobians that are infinite somewhere. Just like complex variables having to have, and I didn't, I think, mention this, but the only complex variable, analytic function, that doesn't have a discontinuity, infinity somewhere or 0 somewhere, well, in fact, you have to have an infinity somewhere for all of the complex functions except for one, and that's the complex variable z equal constant. All other ones blow up somewhere, okay? And a lot of the mechanics problems share that thing. So this has places where things blow up. Singularities, you call them. This isn't going to work. But if I look at just this one, just look at the little x and the little y, I immediately get something that we can call our Jacobian. At least the Jacobian for the variability of the phi and phi. And then we'll tack on whatever it is we have with this coordinate here, big X and big Y, and that's also with a theta, but not a phi. Okay, so I will jump ahead here on this one, question mark notation in there.
So is there a reason, like mathematically, that we couldn't have Jacobian as a rectangular matrix, or it's just not convenient to work with?
Well, then the question is, how would you work with it, you see, because there's, you would have 4 things here, and then what are you going to have for the 4 things here? Rectangular just doesn't, in other words, we can't do an inverse of this, you say. I would say rectangular is a big nuisance, right? Sure, you start out and write it, but it's not going to go anywhere for you. This is not a good thing. So basically, it's a source of a square one. That's kind of way. Now, this is something else that's really not mentioned in books that set up. I usually start with examples that's so simple, the issue isn't there. But this is a bugbear for any sort of thing. Now, one of the things that we actually, what we're talking about this is I really would like to have a good simulation for something that has the mass hanging like this one does, but more than that, that has wheels on it so it can kick. And the funny thing about a trebuchet is if it has a great big mass, it kicks forward. So it actually adds energy by kicking. You see, it doesn't recoil, come back and make it less, it makes it more. So we really need to set a simulator for that and then try it out on a couple of these devices here. So I found that the paper that came with this thing is incomplete and in fact wrong about some things. And it might be worthwhile if you want an article in the American Journal of Physics. We haven't put one in with all this stuff, and I think we probably ought to. And besides, it's getting close to Halloween when you chunk pumpkins, right? It becomes appropriate. Okay, so let's see if there's anything here that I can point at. Otherwise, I'll be pointing at it over there. I think this is good. In any case, there's a determinant of the Jacobian, a thing that you put when we need to invert it in the denominator. So right now we just leave it like that. So transpose relation is also worth, because what we'd like to do is make the kinetic energy out of the dot product of these two, and that'll take care of the kinetic energy for the little guy, and that's the one we care about, but we do need to add to it the kinetic energy of the driver, the thing that's driving the projectile. So we'll be getting the kinetic energy of the projectile, and then we're going to add to that the kinetic energy of the monster that's attached to it. You might be interested to know that some of the trebuchets that researchers have deduced existed, and these things are made of wood, so they rot. But on the many castles in Europe, there were huge circles at points around the rim, which it appeared a trebuchet sat. And they've seen the pieces of them, and from the pieces they deduced that some of the trebuchets carried a big M, and I mean a big M, 30 tons. 30 tons. Big, thing. The idea was to throw a trebuchet from the castle to somebody who was building one and wipe it out, right? So it was a defensive tool. So most of the trebuchets were built by what was available outside, right, if you were attacking. So you usually didn't get to build a really big trebuchet. Siege of Kenilworth is an exception. I'll explain later on how they got their mass. It's rather sad. But anyway, so we got kinetic energy of this and kinetic energy of that. We could just go ahead and discuss that without any further discussion, except that we really do want to build the Lagrangian. Lagrangian is going to be the thing that lets us make an equation out of this that's pretty useful. And we find the Hamiltonian helps us in a funny way later on. So anyway, this is what you do. I'm just giving you a bookkeeping scheme that sort of keeps, getting the right sign and the right algebra as you build whatever function you need for this. Okay. So the raw Jacobian up here, and then finally we got the total KE. That's the Cartesian version. Here is the thing that involves the variables, the two variables that we have. This, of course, involves 4 variables. So we got to do we got to keep this in mind to do a general derivation of Lagrange's equation for a situation where the variables don't quite match. But we're about to make them match. Okay. So it's this that we are going to be doing. This is the xy to theta, and then the other coordinate doesn't count for the big X and the big Y of the driver. All right. So here's where we start, and the idea is to go ahead, get the kinetic energy written there. Get this thing. This is the, from now on we're going to use a gamma to describe the metric tensor that goes with the queer coordinates that include mass. It's big mass and little mass throughout this. Okay, the green thing is the driver, and the red is the thing that's going to be hot and thrown by the driver. And that's the kinetic energy right there. So the idea is to write that kinetic energy as a matrix. That is, take the coefficients that make the kinetic energy and display them as you see here. So it consists of a thing that involves the driver, and then the driven involves these two things, the transposed Jacobian and the Jacobian are sitting there pretty obviously written down. Now, I'm going to go ahead here and manipulate this a little bit. Here's the total kinetic energy with everything in it. Okay, this one includes mr squared here. This one is just dealing with the projectile. So putting them both together makes it, you know, what we want. And there is this thing that's called a dynamic metric tensor, gamma. So it plays a role of G, but it is gotten by scalar products of these partial derivative expressions here. So here we have a coefficient m involving the masses. Okay, these are just reminding us that each of these things are functions of both masses, the little projectile mass and right here the big driver mass. So this is our kinetic energy in that form. And let's see if there's anything we should point out here. Oh, when you're doing this, you check out that your kinetic energy makes sense for singular situations. Now I'm going to catch up here because I see we have a bad font right in the middle there. So I'm going to go ahead up to this point where I presume we won't have a problem with that. So there we are. It's that crazy L that we use so much in physics. In this case, it's like a lever arm there, and this is R minus L, the radius here, wherever this little the R here, and then the distance R minus L is there. Now with the two angles equal to 0, okay, and remember, let's see if I've got that, or the difference of the two is 0. One of them is pi over 2, the other is minus pi over 2. You have an expression that's very simple for this. It's R minus L squared, that's this little radius here, squared times the omega squared. The omega would be the, you know, how much this was moving. And then this one is just plain mr squared omega big R squared. Okay, so that's just checking that these equations work for that case when theta minus phi is 0. And then when they're orthogonal, theta minus phi equal pi over 2. Okay, with a pi over 2 on the cosine right there. That's when cosine is 1, so you get this binomial thing, which is a r squared plus L squared times the angular velocity that's going on with these two, you see. So, you know, when you're building these things, good idea to take singular cases and just check them and see if they make sense in terms of just elementary physics. Because here you have R plus L out here plus that distance there, and that's indeed what you have with this. So this would be the starting, very near the starting point of a trebuchet. If you had to bring the lever down to here, the mass might be sitting right where the dot is. Okay, very close to this state. And then when the thing is fully extended, that may be, if you can arrange it, the maximum velocity of that mass, you see. So those are two extremes that we'll be looking at later using Hamiltonian analysis. The other thing I wanted to show was that when you have them at 90 degrees, okay, then the two coordinates lines, there's the coordinate line for the projectile, there's the coordinate line that's associated with turning this angle, the big theta, okay. There's a 90-degree angle between the two coordinates there, but that's only when that holds do you have a 90-degree angle. Most of the time it's not orthogonal. So these are definitely non-orthogonal coordinates, and we're definitely going to have off-diagonal metric coefficients in every mechanics problem that requires Lagrangians. Okay, so now we're going to derive Lagrange's equations the way we did for polar coordinates, but this time with everything going on a trebuchet. So remember how the first thing you did was say, I'm interested in probably the work done as we have a force times the differential in distance x and y, and this is the Cartesian expression of that, using just F equal m acceleration, ma, Newton 2, for each of the dimensions, Cartesian dimensions, so we can do that. Little x, and this should have been a y here, that's a typo, mx dot dot and my dot dot being the Cartesian forces. So I'm just going to write these in columns here. And then, one of the things that we'll do is use the Jacobian to go ahead and expand each of these differentials into the partial derivatives that we've already calculated for the Cartesian coordinates, in this case the driver, and then in this case the little x and y of the projectile. But in terms of those differential coordinates that we've chosen here, this is a two-dimensional, 2 degree of freedom system. Okay? And then assume these variables are independent. That is, theta and phi are independent. So I can set them to anything I want in these expressions. And if I do that by making d theta equal to 1 whatever, okay, it doesn't matter, you're just going to forget about the coefficients d theta. It'll just be 1, and then completely eliminate the coefficient due to phi. Okay? So here's my expression in terms of Jacobian components and Cartesian double derivatives. Okay? And then if I do want to get the other guys going here, then I get this set right here for my dw, my work expression. All right? So that's the start right there, you see. And this is where we do the Lagrange trickery. You remember that when we were on polar coordinates. Okay? We've got these expressions in terms of the Cartesian coordinates. We've got x dot dot, partial x with respect to theta, right? And what we're going to do is say that is a derivative of the product of x dot and the Jacobian, subtract x dot times the time derivative of the actual Jacobian component. Okay? So we're just using the product derivative to rewrite this product of a double derivative and make it so there's only single derivatives in there. That's the Lagrange trickery, if you recall. We did this with polar coordinates. So, we've got a lemma 1, remember those? The idea that if you had a Jacobian made of velocities, that is a Jacobian representing velocity of Cartesian kind, and then the queer coordinate that went with it, well, that was just equal to the ordinary Jacobian. Remember that? These are key things, okay? And then lemma 2, that was a little harder to prove, but it was that if you had a partial of a velocity, a Cartesian with respect to the queer coordinate, that was just a time derivative of that particular Jacobian component. So using these two, we can manipulate that thing into some. If you don't remember this, it's back in lecture 9, right at those pages there. Okay? So that's what we have to do now. We replace that stuff in there. So step C of the Lagrangian trickery is to realize that I can write these guys, this guy right here, and this guy right here, using that. Okay. Another product derivative, but a pretty simple one. Okay? So that lets us replace every one of those Cartesian expressions with this. Now this one is just involving, here we have mx dot squared, here we have my dot, that's the driver. Here we have the projectile, okay? And then we have it again right there. But you see, when I pile these things all together, I sum, and that's what it is, it's the sum of all of this. You see, it's a 2-degree system, but it's got 4 terms. Okay, and that's what makes the Lagrangian derivatives complicated and actually bewildering. A lot of students have trouble getting this. But that's the deal. You just add up the first and the last column for each one of these. First for this one, okay? And this gives us the definition of the generalized force, which has 4 terms, not 2. It's got 4 terms. It's got the big X and big Y of the driver, and it's got the little x and the little y of the projectile. And we're all dealing with theta right now. We're going to be dealing with phi from this one, but let's just do theta first. But there is the Lagrange equation just involving the coordinate theta of the driver. This angle right there for the driver and the whole lever. Make sense? Okay? And then we do it again. Add up everything in the red square here, having to do with phi. So there's the first really non-trivial Lagrange equation right there, because it involves the angle phi, which is a function of both the theta and the phi. Okay? And this defines a generalized force. So when you say covariant and contravariant, we want to respect that. So we'll be writing these things with indices down, these forces here, with indices in the covariant position. And this is a covariant sum. It's just that it's got 4 terms in it, not 2. And that's why you think, that's why we like to think about that rectangular Jacobian at least a little bit, because the force involves it. But once you've done that, everything here is a function of phi and theta. And there's no x's and y's left. So we have finished the derivation of what I call the 4-wheel drive garbage truck Lagrangian. This one works for all sorts of things. It'll work in a rotating coordinate system. There are all kinds of things you can get away with this. But one we really want, of course, is to make this a gradient, right? Then you get the Lagrange equations that you see, when you Google Lagrangian equation, that's what you get, right? But this is the one that's, as I said, 4-wheel drive garbage truck. You take a load of crap and drive anywhere. So that's our force equations right there. That's the one that will always work. And we're reminding us what the force is. It is a function of the angles as well as the radii, which are not variables here. Okay. Now, one of the things that's good to do, and I see that L is the thing that's giving us a headache here on this particular computer, mainly. I will go ahead on the other screen here so that we have it displayed properly. L doesn't seem to be causing problems for this one. In any case, all of the force that is applied by outside is gravity here. We're not taking into account any sort of friction or anything like that. We're pure physicists. We don't believe in friction at this point. But the idea is to put the gravity on, that is Fy here, that's big Y for the big mass, little y for the little mass, okay, are giving us torques that are competing torques on the main beam there. Okay, and then there's a torque, and I'll go ahead and put it here, a torque on the throwing lever, L, that's what that is. And it's also obscured by the fact that the shelf here has a warp, and it's sort of hard to see that. But in any case, I think we've got everything we need here. Now, one of the things you do is you check to see if this is making sense. And at first it looks like one of those is kind of weird. That is there a sign error here? And the answer is no, because the beam is in the minus position. So we end up as shown there with this sign minus here and this one a plus. And the same, I think, can be said for the one down at the end. So there's plenty of opportunities as you go deeply into Lagrangian or Hamiltonian to check that you've got the right algebra. Okay, now let's look at the canonical momentum and the functionality of the metric tensor. We've written the kinetic energy this way, and this is its actual GCC value or expression. And we're going to be interested in applying Lagrangian equation in the way it comes to us for just defining the momentum. So P, that's going to be our generalized momentum, partial derivative of the kinetic energy with respect to Q dot. So I'm going through here and taking partials with respect to theta dot. And then there's another theta dot there. So I just really get two terms out of this thing. I get this thing right here with a phi dot and an MRL, product of the radii and L. That's kind of like a Coriolis effect right there. And then this is sort of an inertial effect for theta dot right there. So we're seeing angular momentum, this generalized canonical angular momentum being given to us rather easily. And then there's one that goes with the projectile as well. Okay? And the projectile has a phi dot here and here, nothing coming from that term. So we just get, again, two terms, but they're involving ml squared phi dot. That pretty well makes sense for contributing angular momentum. But then we got this Coriolis term too. So it's a product of involving theta dot and the geometry. Now, that should be important. This is something that we'll see for every Lagrangian equation, however terrible it might be. Having the momentum be given is just a product of this metric thing and the velocities. Okay? And I'll give you a matrix proof a couple of pages ahead here. But this is really key. This is what makes the analysis simplified. And it's something that will happen in Unit 3 using the full tensor notation. So I'll give that index thing, index proof here. Now, once again, the index rule that applies to tensors here, we've got a covariant quantity, and then there's the contravariant queer coordinates with their indices up. And we're summing because they're repeated on the same side of the equation, both over J and over K. Okay? So, this thing right here, the partial derivative with respect to Q dot, gives us two terms, each within a half. Okay? And it's kind of like the half and half in our complex variable analysis. Those two are really the same. And the reason they're the same is because this matrix, this metric, always symmetric. Okay? That's definitely true of the geometrical one, but it's also true of the one that has masses in it as well. So that just gives us, and here I've changed the dummy indices so that I can express that just as that. So that's the proof of that. Now another way to prove this is kind of a matrix proof. If you're thinking in terms of matrices, you can go ahead and write the kinetic energy as a bra, then this matrix here, and then the ket with its partial derivative, all right? And just write that out and see how it comes. Again, a half and half, but you can see those are the same right away, and you get this. So that gives you a proof of this theorem about momentum being the metric times the velocity. Okay? So this key theorem works even when you have the degrees of freedom that we have with this problem. Now here I'm just kind of displaying all the things that could have bugged us about this system because of its not being orthogonal, right? First of all, we're going to have, and this is without friction, we're going to have lots of force being applied right here, called the steadying force or the support force. Okay, so some big vector, as this thing's moving, is going to be sitting right here. And if this thing has wheels, that big force is going to be important because it will be driving it this way. And that's in fact what happens to the trebuchet. If it has wheels, it moves in the direction of the throwing. So it's kind of like a pitcher getting extra speed by taking a big step, big linear step forward toward the batter, right? So the trebuchet does that. And that's what we've left out of the analysis here. And it's worthwhile, I think, that we should put it into that deficit in our simulation ability. So, anyway, and then there'll be forces applied to this pole. We have completely ignored that except for the gravitational force, but there'll be other forces being applied there. And then don't forget the centrifugal force, which is actually in the equations that we've written here. Then there are constraint forces. Something's holding this ball always on a circle around this point. Okay? And then there's Coriolis forces depending on the relative velocities of this and that. Okay? And a centrifugal force too. So there's all this stuff working on these things, yet this is the complete set of equations for it. Now if you're applying real forces from outside like we are with the gravity, well, we add those. But we put a big zero here, and that's something we need to talk about later on as we talk about constraints in general at the very end of this unit. But these are stresses and support forces that do no work, first of all, so that kind of writes them off right away. But then still, it's a bit of a geometrical mystery of why we get to ignore all of those arrows except for the ones that are really driving it, and ignore the things that are holding it together. Well, that's, I think, an important thing to see. These are the Lagrange force equations again. Here, we haven't put the potential on. We need to do that because this is a conservative force, this gravity, on each of the masses. Okay. Now, if I can write each of these as a partial derivative of a potential, and I can, it's just mg height, big M g times that one's vertical location, and little m g times that one's vertical position. So we're going to do that. But please remember how simple these equations are. First of all, the definition of momentum, then the equation for its total time derivative. To get this one, you take the dot away from that one and put it there. Right? So, to my mind, that's the beautiful way to show that. Okay, let's see if, yes, we need to talk a little bit. We have a few more minutes. Let's get a little bit into Unit 3 stuff before doing any more algebra here. These are two trebuchet configurations with the same coordinates, x and y. One of them is left-handed. The other one is right-handed. Okay? This is a little bit of topology that is part of so much of our physics now. Topological insulators on down. Okay? polar coordinates really have this issue. You go in on this one, and you come out on a different sheet. So we've already seen this, it's just it wasn't terribly obvious. This one really makes it obvious that you need to consider two topologies. So in Unit 3, these are figures from Unit 3. Okay, this is just the first section, the second figure. This is the torus, or the manifold, that describes all of the possible Trebuchet positions. And here, and this is something I want to ask you to do later geometrically, but what you can see here is if I hold, this is theta equal 30 degrees. Theta is constant, okay, so I'm holding the position of the main arm relative to the laboratory fixed, and I'm varying the phi, okay? So this is Q1, which is our theta, equal to 30 degrees. It's being held constant, but phi is varying. And here it's minus 105 and so forth, okay? And it actually goes and makes a circle. But we only show half of it. We show the top plane where the thing is still left-handed. This is the left-handed surface. Here's the right-handed surface. Again, Q1 is a constant, this time at minus 60, okay? And as I run phi around its circle, well, it would be a whole circle, which would include that circle there, okay? But I'm just cutting it off sort of at the equator of the torus. So there's all the places it can be a right-handed configuration. Here are all the places it can be a left-handed configuration for a particular angle, theta equal 30 degrees, okay? And remember, this is 0. There's theta equal 30. I turn it counterclockwise, so it's positive 30. Right? So this is just a map to get you that, and this is what we'll be studying in a little bit more detail in Unit 3, but we can look at it right now because I've already assigned to you some stuff that involves the covariant and contravariant vectors. If you want to get your homework done early, you ought to take a look at this.
Dr. Harter,
Yeah.
how do you know that it's left-handed or right-handed? Is there anything, like the smaller mass could, in principle, spin either direction on either of those sides, right?
The singular points mark a boundary between being one kind of thing and another, okay? One of the singular points is right there where the mass is tucked in.
Okay.
And the thing I guess I didn't mention was that the metrical tensor goes either infinity or 0 for this singular case. Now the other one is here. So there's the starting place that we talked about, that's one, and then the throwing place where you probably want to let it go because it'll be going fastest, maybe, okay, up there, all right? So between there and there, this thing is left-handed. In other words, I come up with my hand and just put my fingers on this and my heel of my hand on the main bar. That's left-handed.
Okay.
The other way is put my right hand in here. I can't bend it this way without breaking, right? So it tells me right away that's right-handed.
So it's determined by whichever is the smaller angle to the
Yeah, yeah. But it is a handedness, right?
Yeah.
In the sense that I would use my right hand to describe this one, I'd use my left to describe that one. That's the best answer I can give you on, determining handedness, but we'll see other examples that we talked gyroscopic motion where that's an important distinction. Does that make sense? Everybody see that? Okay. Okay. So what we have, and this is what I'm trying to, is that you can take any curvilinear coordinate system, however crazy, and smash it onto a Cartesian plane. In other words, what I'm doing here is I'm just literally plunking down the queer coordinates Q1 and Q2. The Q2 is this way, that's phi. Q1 is this axis right here. So I'm just taking the thing down and putting pictures of the trebuchet that it goes with a particular value of theta and a particular value of phi, say both 90 degrees, okay? Then I'd be looking at that thing right there with a little ball inside there. And this is a boundary between left and right. You see, it's just passing through the beam, right? To come out on the other side and change its handedness, you see. So on this side, I'm seeing left-handed, right? When I put my hand on that little guy right there, that's left-handed, right? And then I need my right-handed turned over to get that guy. So all these in here are right-handed trebuchets, and then they become left-handed again over here. And this just goes on forever, right? In all directions. So this is an infinite plane that has the trebuchets of manifold repeated multiply many times. But inside, say, now we're looking at a right-handed configuration. So it's the top of this torus, okay? But this is I mean, your eye fools you, and when you see this, you say, oh, that's a three-dimensional drawing. This is higher than well, yes, it is if you want to do this kind of drawing. But here, everything is in the plane. Once again, we've got an example where it looks three-dimensional, but it isn't. And this is really the angle right there between that guy and that guy. And you see that they only get to be right angles right here near the top of this surface, you see. And then everywhere down from that, they even get very singular right in here and very singular out here, where the area is subtended by the unit vectors collapses. So here's your covariant vectors, the ones that go along. There's an E phi that goes along the dimension phi. And this is the E sub theta that goes along the dimension theta, okay? And then the question is, how big are these, you know? Well, they're about, if you do it right, that is like this, they're exactly the scale. In other words, if you let them be 0.01 in length, so that be your unit, okay? This is 0.1 distance right here, and there's 0.01 distance right there. Those are the actual vectors, the ones that frame the cells at that point. Now this one frames this cell at that point, but you see, I'd have to make the cell really small in order for it to be obviously framed. Here it's deviating very quickly away from that, so I would use whatever that distance is, centimeters, to characterize the cells, and that would make a much finer grid that would all have little parallelograms in it with the sides appropriately scaled. Okay, covariant, contravariant. Here's the Kajobian, here's the Jacobian. Let's put that above on the screen there, just to have the proper vision. No problems with fonts on this one, so we can use either one, okay? But the basic idea is that these vectors, the contras, the ones that that you have coming here from the rows of the metric, okay? And remember the Kajobian metric, the one that has the contravariant bases, has a determinant of the Jacobian. This one does not have that, okay? But this one does. And this one, you use the columns. The columns of this one, these are like the kets. These are like the bras, the horizontal vectors that come out of those two partial derivatives, giving me this. And each of those are inverse things, so they have the determinant of this matrix here, minus RLS cosine theta sine phi, and then subtract sine theta cosine phi, also RL. Well, that makes us a sine of theta minus phi. And you see you've got a problem when theta are equal to phi, right? Or if theta and phi minus 1 gives you a pi, right? This goes to 0. So this blows up. Then you could have theta minus phi be 90 degrees, okay, and you get to another interesting point. But there, you know, it's well behaved. Now you're out in the middle of the activity zone. Okay, so this is contravariant, covariant. Now, remember, these are the guys you're going to have to work with a Hamiltonian. This is simpler. He's got this extra determinant of messing things up. So, I wanted you just to see what, you know, the real professional classical mechanics talk about a tangent space. Then they're talking about these vectors that are covariant, not these guys that are going wild, perpendicular to the lines of the coordinates. Okay? That's called a normal space. It doesn't mean it's not normal versus abnormal. This is just normal in the sense of perpendicular. So these guys, these contras, go contra to the coordinate lines. But anyway, they make an array too, you see. It's just that this one is nicer in the sense that it's the one that lies right on the torus. These guys go normal to it. Okay. Now you can write a vector either way. You can write a vector in terms of, I'm going to go ahead and jump to this one right here. You can write a vector just using the basic thing. The contravariant vector is written in terms here of the other, another coordinate system. If there was another coordinate system that we were using for some reason, and we will be doing that actually, this is a coordinate transformation from the contravariant vector we got from just the initial Hamiltonian or Lagrangian, and these are the some other barred coordinate system. Then you need to have this super Jacobian that is one kind of queer coordinate system versus another. So far, all of the stuff that we've written down here has been a Jacobian that involved the queer coordinate system and Cartesian. Okay, but if you have another curvilinear coordinate system, then that's a transformation that you need to think. Now, the actual lengths of vectors here, like if you do a projection of the vector that you're writing in contravariant coordinates and compare that to a vector that you're writing in covariant coordinates, it's very, very different, you see. This distance right here, okay, that's what I'm going to be asking you on one of the problems to identify. Identify in terms of the components of the vector and its metric. And usually it's a square root of a metric coefficient. In fact, the diagonal one, because that's what the g's actually give the lengths of those things. So all of this stuff this applies either to contravariant or to covariant. There's a typical transformation of components that matches that of the vectors. You should be able to prove that fairly easily. But whenever you want to do a coordinate conversion in one of these things, write the vector. If you want to do a transformation of this vector, write its partial derivative down. That's its definition, partial of r with respect to q, super m. That makes you a sub m here. And then you do what I call the chainsaw sum rule. You chainsaw the partial derivative in half and slide them apart either way. And then you put in whatever kind of coordinates you want to make your transformation to. Say the bar, q, u bars. Just stick them in there, sum over, in this case, again, 2 dimensions, whatever they are, and that's your transformation rule. There's the transformation coefficient. There's the new covariant vector, E bar, okay, covariant, with covariant indices associated with that particular thing. And there's the super Jacobian. So that makes it really easy. Once you've got that, then the components have to do the same, and that's something you should prove on your own easily. So once I get this, and you see this one is backwards. You see it's upside down from this. It's inverse to it. Does that make sense? That's the bookkeeping that I wanted you to see. And this covariant projection here, I think we'll stop with that. Okay, that's the covariant projection. See, the actual distance that you're talking about. You project this thing onto the covariant, right? Well, you have to divide by the length of this. The length of this is that. That's the annoying thing about GCC, right? When you do a projection, you got to remember the length is given by the diagonal components of the metric. Okay, now this little chainsaw thing right here, that's analogous to your Dirac notation where you stick in what they call the projection operator sum, right? The analogy is well taken between Brodketz and covariant and contrarian. Okay, well, there are a couple of things that I'll just let you study and read about. This is just sort of a review of what we've already said. And that's the key thing for lengths of either one of these vectors. 3 dimensions we'll be talking about that soon enough. You have an example in the homework that involves 3. Doesn't involve Jacobian so much, but still, that's what you're working with as far as the differential calculus goes. Okay. We'll take on the Irish and the German approach to mechanics for this problem, the Trebuchet, on Thursday. Okay.